Hello everyone. Today let's solve the problem number 212, word search 2. So we have already solved a word search 1, right? So this is similar to the word search 1 itself. Let's see. So what the question states here, we are given an m into n word. You can clearly see here, we are given an m into n word of characters and list of words of characters and list of words. You can clearly see here, right, of characters and list of words, right? So we need to find all the words that can be formed on a board by connecting the adjacent letters horizontally or vertically. We cannot consider diagonally. So this we have to keep in mind. We cannot consider diagonally. So we have to consider the adjacent letters horizontally or vertically. Each letter can only be used once per word. So each letter can be used only once per word, right? So this one we have to keep in mind. First thing is, we cannot make use of the adjacent letters. We have to make use of the adjacent letters horizontally or vertically. We cannot make use of the letters diagonally. That is one thing. And each letter can only be used once per word. So this one we have to keep in mind, right? I hope this is clear. I hope the question is completely clear. So here, let's come to the example. Example 1, what they have given here. So input board, they have given this one, OAANETAE, all the rows, the letter that start with the first row or 0, 0 or the first row. They have given that itself here. OAANET, this one, IHKR, finally IF, IV, right? So the words they have given here is oath, pee, eat and rhyme. You can clearly see here. So first, to store the words, we can make use of the try here to store the words, right? To store the words, we'll be making use of the try. And to search the word or to fetch the word, we can make use of the this one, recursive DFS or DFS. Let's call it DFS. Then let's see the this one approach. Basically, when we consider the example and this example itself, and dry run this one accordingly with the approach, right? So this one, what we can do here, they have given oath here. First, we will start from here. So we can either move horizontally or vertically as per the question they have stated, right? So here O we have, we can just move here horizontally. OA we got, then vertically we can move one step, because here this fails because we need T, right? So then we need H here. So we will move down. So oath we got. So here this one is fine. So next let's go to P, right? They have given P here. So we will start this one from P. So P is not present at all in the this one grid. So this will be false basically. So this we got oath, and the P fails miserably because P is not present in the grid at all. Next, let's consider eat here. So E here, we will consider this one. So A, they have not given order, right? So here we can move left here from this one step. So next we can move left itself. So we cannot, if we move up and down here, it fails, right? So this one fails. So we'll move left. This one will be eat. So we have found this one eat here. Oath we found here, this one, and eat we have found here. So this one we have got eat as well as oath, except that P got miserably failed because there is no P. The first letter itself is not there in the grid. So let's come to the rain here. Rain R we have here. We'll start from here. So A, we don't have A at left, up, down, this one, right? So right, we don't have any of this thing at all, letter at all. So this is 4 into 4 grid, right? So this fails as well. So only one R we have in the grid. This fails as well. So O then eat we got here. Same goes with the example 2 they have given here. So you can clearly see A, B, C, D. So words A, B, C, B they have given here. So another B we don't have in the grid at all. So this fails completely. We have to return empty array in that case. So that's what they have given here. So I hope the question is completely clear. So let's see, let's discuss the approach. So as I have said, we can just store the letters in the tree, and for searching we can go with the recursive DFS with backtracking. So this will be the approach mainly we will be going with. So let's discuss the approach. Let's dry run the example. This one, first example they have given here accordingly with the approach. So let's discuss that one as well, and then followed by edge cases one by one. Let's discuss edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, let's go with the approach. Here, let's discuss the approach step by step. First thing is, we are making use of the data structure try with DFS, try and DFS, or try with DFS, right? So that's what we'll be doing. So I have considered the same example that they have given in the question, right? So the first example that they have given in the question. So what are the words that we need to fetch? Basically, among the letters they have given here, we have OAAN in the first row. In the second row, we have ETAA. Third row, IHKR, and the fourth row, IFLV, right? So what are the words that we need to fetch here, whether they are present or not? Oath, pee, eat, and rain. These are the words that we need to fetch in the word. So I said we'll be going with the try and DFS. Let's move on with the step 1. In the step 1, what we will do, we have to build the try structure. So let's build the try structure here. So just give me a second here. Yeah, let's build the try structure. So here, when I say build try data structure here, what we have to do, we construct a try from the given words. Why we are doing that one? Because for the efficient searching, for the searching we are going with the DFS, right? So we are constructing a try from the given words for efficient searching. This we have to keep in mind. The try structure will basically look like this. So I can just give here, we know that initially we'll start from empty root, right? So this one will be first what we have here. So just give me a second here. So I can just consider here in this way. So first row what we have, what are the things that we need to basically, so just give me a second here. So yeah, what are the words we need to search here? Oath, pee, eat, and train, right? So we can clearly see here one thing is P is not present at all, PEA. The letter P itself is not present. So we are ignoring this one in the try when we are building the, or when we are constructing the try, right? So let's go with the try structure. One is we have oath. Basically, we can just write it in this format, OATH. And the second one is eat, right? EA and T. This is fine. The last one is rain, RAI and N. So we have constructed a try from the given words. Why we are doing this one? For the efficient searching. So just keep this one in mind. For searching, we'll be going with the DFS. For the efficient structure, for the efficient searching, we are building the try structure. This is the step 1. Let's move on with the next step, or the step 2. Here, we are performing the DFS on each cell. We will start with O. We need, we are searching for oath, this one, what do you call? Eat and rain. So as P was not present in the P, the letter P itself was not present in the grid, we are ignoring that one while building the tree itself, try itself. So we are searching for this one, oath, first. First, we'll go with O. So here, if we go down, this is ignored basically, because we need A next one, right? So this one, 0,1 will move. So A we got. So now next we need T. So if we go here, this one, we have A. We don't need another A, right? So let's go down. We got T here. So one step we can move horizontally, vertically. So we can either move vertically, this one, up or down, left or right, one step. when we are performing the DFS, right? T. So if we go right side, we have A. We don't need A. So we are in searching of H. Basically here we found at 2, 1. So we have oath now. So oath we have found, right? Let's go with the E. So here we'll come to this one. Basically we'll start with this one. Again we'll start with this one 0, 0. So here for it will come this one E. So here we will move A. Yes, A is present here. So we will go with A, E, A. Now we have this one, because down we cannot go. R is present. This doesn't satisfy the condition. Here when we go for A, down we cannot go, and up also we cannot go. This does not satisfy the condition because we need T here. So T is present here in this case. So it is present here. Oath is present here, right? So the last word we need is rain here. Rain, R is present here, no doubt, but A is not present here, here, or even up at all, right? So we have only one R basically. So we have only one R. There is no another R present in the this one. What do you call this one? Grid, right? So this does not satisfy the condition. This fails for the rain. Only eat and this one oath we found here. So that's what we will be displaying in the form of output. So we found oath and eat through the DFS and try. So what are the things we found here? Oath and eat, right? So that's what I'll just come here. The output that we got here, I'll just write oath within the string and eat. This is same as the output that they have given in the mentioned in the question. So this approach works absolutely correct. Two simple steps, right? So after performing this one, basically what we will do here in the step 2, I stopped here, right? So this one we found oath and this one eat. For P and drain cannot be found, so we ignored that one. So during DFS, we need to observe one thing. During DFS, we temporarily mark the visited cells. After suppose we when we first visit the O, right? So we will mark this one as ash. Next, when we go to A, we will mark this one as ash. T will mark this one as ash. So when we move here also, we will mark this one as ash. Whenever we move to the each cell, then we will mark that one temporarily as visited with hash to prevent the reuse. To prevent the reuse, we will be we'll be marking them with hash, right? So that's what we'll be doing. If a try node is completely used, we will delete it. So if try node is completely used, then what we will do? We will delete it. So why we will delete this one? If a try node is used, we will delete it, right? Why we are deleting this one? Just for the sake of memory optimization, right? For the sake of memory optimization, we will delete the try node if it is completely used. This one we have to keep this in mind. This comes under the backtracking. So we temporarily mark visited cells as hash to prevent the reuse, one thing under backtracking. And if a try node is completely used, then we will delete it for the memory optimization. These two steps come under the backtracking. So I hope all the steps are clear. 3 steps. One is building the try structure, and second one was for this one, perform DFS on each cell, and third one is this one, performing the backtracking, right? I hope all the 3 steps are completely clear. Now let's start let's discuss the edge cases one by one. So here let's discuss the edge cases one by one. First one is when no words found. It is for the condition when no words found. So board, we have input OAAN, AETAE, IHKR, IFLB, right? So we are going for the word. We have to fetch the word or search for the word they have given here. We have considered A, B, C, D. So you have to perform DFS, right? So here B and C, B, C, D are not present at all. Only A is present. So this is we can just ignore this one. So the output will be here empty array, right? So here this is for the condition no words found. So we consider this example, right? Let's move on with the next example. This is for the condition. Just give me a second here. This is for the condition. This one, single letter words. So I'll just give here. Just give me a second here. Yeah, single letter words. This is for the condition single letter words. We have A, B, C, and D. So basically, we are going for the single letter words that are present in the board, right? So here you can clearly see we can consider this one. First, we can consider this one A. So and then they have asked us to fetch A, B, C, and D single letter as the word. Then we will go for the B. B we have, then C. So this one, and then D. This one. We have the output for this one, right? So this satisfies all the conditions here. So single letter words are present in the board. Basically here the output will be in this case. Sorry, what happened here? So the output will be in this case A, B, C, and D. Each letter as a word, it satisfies the condition, right? It satisfies the condition as a word. Each letter we are considering. So this is fine. Let's move on with the third edge case. Nothing but here all words are found. So let me give here all words are found. We are considering for the condition all words are found here. So we have to fetch for ABC, ADG, and CFI. So here, so we are performing DFS, right? So here ABC first will go here, then here ABC we found here itself, right? So this one, this satisfies the condition ABC. Next ADG, A. So here we'll start with A itself, then followed by D, then followed by G. So we can move either horizontally or vertically one step, either up, down, left, or right, right, when we are performing the DFS. So this satisfies the condition as well, ADG. So next let's go for the CFI. C will start from here, C followed by F followed by I, one step down here, right? So we are ignoring this one. So this is fine. We have found all the words here. So this satisfies the condition. Basically all words are found. So the output we can consider here as, so I'll just consider here ABC. We are pushing all the things. So here ADG, and the final one is CFI. This is fine. So I hope all the edge cases are clear. First edge case that we went with here is no words formed. Second edge case we discussed about the we had discussed about the single letter words here. The third one was for all words are found here. So I hope all the edge cases are clear here, right? So next what we will do, let's discuss let's write the code. I'll explain the code while writing the code itself, and finally let's discuss the complexities of the code that we have written. Now let's start writing the code. So let's start writing the code. So we have to store the results in the form of array, and also we are starting with the root of the try. So root of the try has to be empty, right? Whenever we are dealing with the try, initially we'll start with the root of the try, nothing but the empty. So that one, for that root will be considering object, and we have to store the results in the array, right? So I'll just give here that result equals this one, and root, let's initialize this one to the empty object. So this is clear. I believe this is clear. Next step is, first step, we have to build the try from the given words. That's what we saw in the approach. So this is simple. I'll just give here let w of words. This is fine. So within this one, we are starting from the try root always, as I have said. So I can write in this way, let node equals root. This is fine. So the next step is, we have to create the nested objects for each character. For the each character, we are creating the nested objects. This is important. We have discussed this one, but still keep this in mind. We are creating nested objects for each character. I'll make use of for loop. I'll consider individual character of words, nothing but W we have right considered. So I'll just give you node equals node of individual character or this one empty object. So this is fine. We are just creating nested objects for each character. Next step is we have to store the word at the end node, right? So we are storing the word at the end node. End node, we are marking that one as end, right? So we are storing that word at the end node. I can write in this way. I can articulate that one in the form of code like this. So node dot word, I'll just give here W, right? This is fine. This is the first step. Nothing but what we have done here. This is nothing but building the try from given words that we saw in the approach, right? So if you remember, so next thing, step 2 was we have to iterate over each cell in the board. So to perform the DFS, we have to iterate over each cell in the board, right? So for this one, before writing this one, before the iteration or before iterating over each cell in the board, so here we need DFS. We are going for the recursive DFS here. So we have to first consider the helper function, right? I'll just consider the DFS helper function here. And also, if you remember, we are going with the DFS for backtracking search as well. So the third step was backtracking, right, in the approach. So we are going with the DFS function for backtracking search. So I'll just consider here function DFS. This is before iteration. We need this helper function for the recursive DFS, second step, for iterating over each cell in the board. So we need DFS, this one. For this one, we are writing the, we are considering the this one helper function, nothing but DFS for backtracking search. So I'll just give here, let me pass here board I, J, node and result as parameters. This is fine. So first step is we have to get the character from the board. Whatever the character that we have, individual characters, we need to get that from the board. For that one, I'll just give here, let's see, equals board of I. So I'll just I dot. So if I and j is present, so we'll just check I and let's write j here. This is fine. We are just getting the character from the board here, and from, I mean, in the previous in the previous line or in the line number 11. So now we have to return if out of bounds or not in the try. In that case, we have to just return nothing. We'll just give return in this case if out of bounds or if it is not, if the character is not present in the try, sorry. So character not present in the try or out of bounds. So if node of character, this one, see, then what we will do, return. So this is fine. I hope these two lines are clear. Next, what we will do, we have to move to the try node. So I'll just give here, let n equals node of C. This is fine. So next step is, if the word is found, then we have to add that one to the result array, right? If here, if we find this one, suppose if we have found the OATH here, oath, we are considering this example, we have to add the oath to the result array right here. So that's what we are doing in this step. So I'll just write the simple if condition here, end dot word. Then what we will do, we'll just push the result. This will be end dot word, comma, end dot word. Here, let's initialize this one to the null. If the word is found, then we will add to the result. Next step is we will mark the cell as visited. Once we have visited the cell, then what we will do, we are marking that cell as visited. I can articulate that one in the form of code like this, board of ij equals, let me consider this one, hash. We are just marking the cell as visited. Finally, we have to explore all the 4 directions to find the word. Either we can move up, down, left or right, right? We have to explore all the 4 directions to find the word. So for that one, I'll just be making use of the recursive function here, this one, DFS itself. So this one, let me write board I plus 1 j comma n. This one will be result. This is fine. So let me copy the same thing here thrice. So let me change this one I plus 1 to here. Let me change this one to I minus 1. This one, let it be I itself here. Let me give here j plus 1. So we have to explore all the 4 directions starting from up, down, left and right. So the last step here, this one I have considered j plus 1, right? Here let it be I itself. This will be j minus 1. So I hope this is clear. This step is completely clear. Next step, what we are doing here, we have to restore the original character. So for that, this is simple board of ij. Let me give this one to C. We are just restoring the original character here. So simple, right? So next, as we had discussed, we are optimizing the try memory. So while discussing the approach, I said one thing. So in the third step, if you remember, so during DFS, we had temporarily marked the visited cells just to prevent the reuse. Nothing but this comes under the backtracking, right? So if a try node is completely used, then we will delete the node. Why we will delete that one? Because for the this one memory optimization, right? So that's what we'll be doing here. So we will optimize the try memory. So let me give here object dot keys. We are dealing with the keys, right? So I'll just go with the object dot keys. So we are dealing with the objects here. Root, we have initialized this one to the empty. So empty object. So we can just go with the object dot keys here in this case. N, let me pass n here. N dot length. Then we have to delete node of character. See, we are just optimizing the try memory here. I hope this is clear. This is it for the DFS function. I'll just come here to the main function now. So let me come here. This is just the helper function, right? I hope this is clear completely. So next, let's deal with the step 2 where we had left. So we have to iterate over each cell in the board, right? So let me give here for like I equals 0. So what is happening? This is fine. I equals 0. I less than length of the board here. Let's increment I. Oh, this is fine. So next, let's go with the same thing for j. Have row and columns, right? So j equals 0. J less than, this is for the column, j less than board of 0 dot length. This is fine. Let's increment the j here. This is fine. Final step is we have to call the DFS for each cell. So we have already written the helper function DFS here. We are just calling the same DFS for each cell, right? So I'll just give here DFS, and what are all the parameters that we have here in the DFS? So board, same thing, board, ij, root and result. So instead of node, we will be considering from the root here. This is the main function, right? This is not the helper function. I'll just copy the same thing. Instead of the node, we are starting from the root, as this is the main function. Within the main function, we are considering this one. So we are just iterating over each cell in the board within the main function. So we are just calling DFS for each cell here in this one, board, ij, root and result. Root instead of node because we are considering this one within the main function. I hope this is completely clear. Let me format this one once and let me hit the run button. So wrong answer. We are getting the output undefined. So let's check. So what mistake I have done here is, simple thing here is, I did write the second step here, but I forgot to write this one here. So what do you call here? To forgot before we completely forgot, we have to return result here, right? We are storing this one in the result array, output, basically this one here. So this one I completely forgot. So I'll just give here. So this one has to be, I have misplaced the, so sorry. Just give me a second here. This one here, I have misplaced the bracket here. There should be one more braces here, bracket here. So I'll just place the bracket here. So after to this one, we have to return result, right, within the main function. So I'll just come here, return result I'll give here. So this is helper function. We are just writing that one outside the main function. So we are just making use of the helper function DFS here to perform the DFS right here. So this one I forgot, totally forgot. Sorry. So yeah, this is fine. Let me format this one once and let me hit the run button. So you can clearly see now the sample test cases are getting passed here, right? So I hope this works. So let me hit the submit button. So yeah, I didn't return anything. That's the reason it was giving me undefined. So here you can clearly see all the test cases are getting passed here, right? So the code works absolutely correct. So next, let's discuss the approach. So let's discuss the complexities of the code that we have written. So the approach that we went with here is try and DFS along with the backtracking, right? Try with the DFS, right? Or you can just say try with DFS itself. So along with the backtracking. So what would be the time complexity here? So overall time complexity here would be big O of n into m into 4 to the power of L here. So why here time complexity here is big of n into m into 4 to the power of L. N is nothing but here length of the words. So length of the words, we saw this one in try construction, nothing but big of n, right? So this is n. So what is m then? Then m is nothing but the total number of cells in the board. So n into m we are considering. So why 4 to the power of L here? Because L is maximum word length. 4 to the power of L is the worst case for the DFS search, right? So that is the reason we have got 4 into 4 to the power of L here. So overall time complexity would be either you can consider m into n into 4 to the power of L or n into m into 4 to the power of L. This is fine. I hope the time complexity is clear. So what would be that space complexity here? The space complexity would be here big O of m plus n. So why here the space complexity here is big O of n plus m? Because n is here, n is nothing but the try storage here, right? So I'll just write in this order itself. I'll just make this one n and m. So here n would be try storage and m would be this one recursive DFS stack space. We are making use of the recursion here as well, and here as well. We are making use of the recursion. So recursive big of m, nothing but the recursive stack space, and this one for the try storage. So overall space complexity would be big of n plus m. So the overall time complexity would be big of n into m into 4 to the power of L, and the overall space complexity would be big of n plus m. I hope the solution that we wrote is completely clear along with the complexities that we have discussed. So for now, this is it. Thanks for watching, guys.